Hello, welcome back. So in this session, we're going to be working with vertical projectile motion. That's what we're going to be dealing with. So it's just vertical projectile motion. Just grab a pen there. So we're working with vertical projectile projectile. I'm hoping my spelling allows me there, but that doesn't feel good. I should be J motion. There's not much to explain here but the fact that they're just general calculations. This honestly feels like mathematics literacy to me, but anyways, what you have to know beginning this question is the concept of a projectile. A projectile is an object under put this not rather an object under, but an object in free fall. This is just an object in free fall. Dash, what is free fall? I got you. Free fall. Free fall is the concept where an object is under the influence of gravity. Only gravity. So if I throw an object, that's not a projectile, but if I release it from the top of a building, I've not applied any force, I've released it, then it's a projectile because I have not applied a force of any magnitude over it. That's the idea. So all these general calculations for vertical projectile motion, we mainly use our equations of motion. Now note to self that this is vertical projectile motion, not horizontal. So we won't be working with the values that have x. So all these values here, we do not work with those. We only work with these formulas there. Okay, we only work with those that have a y, because we're working with vertical. For instance, this one can work, not the x. In this case of this one, this has an x, this has a y, I'll take the x. And for this, I'll take this one. So no x's for vertical projectile motion. Let's look at some practice problems. Let's take this arbitrary question, for instance. So in this question, we're given a cricket ball. So a cricket ball of mass 156 grams is dropped from point A on a tall building that is 15 meters high. It strikes the concrete pavement and it bounces to a maximum height of 4 meters. So that is illustrated in that sketch there. Then the question that starts first is calculate the velocity of at which the ball strikes the pavement. So I have to choose the relevant formula that works there. At which the ball strikes the pavement. So it is thrown up and then it comes back and strikes the pavement. So I'm looking for a formula with a final velocity, and I'm looking for a formula that deals with projectiles. So this formula would be sufficient for that. However, this formula does not have a final velocity. It instead just has an initial velocity. So that formula doesn't work. And this is for uniform velocity, so that would not work. So I would have to apply that formula there. So to answer that question, so we're chilling at number 1 now. So I'll start off with the formula. That's just the vf squared. That's equal to vi squared plus 2, and I've got my acceleration a and delta y. And remember, my a is gravitational acceleration. That's just 9,8. You know this. So what's my final velocity? I don't know. I'm trying to figure that out. However, my initial velocity is 0. It was firstly at rest before it was thrown, right? Plus 2. My Gravitational acceleration is a constant 9.8. Okay, and then I've got 15 for my height, my maximum height. Then we let the calculator do the work. So for this, I'm just gonna grab the calculator to do that. There he is. There is the good boy. All right, so for this, I'll just go in and say that's just 0 squared. Why should I bother saying 0 squared anyways? That's just 2 multiplied by a 9,8. Okay, not 98, that's 9,8. What did I press? Ooh, it actually has hyperbolic function. That's really cool. Anyways, 9,8 multiplied by 15 as well. So 15. And then hit the equals. We've got 294. Nothing fancy on that one. Nothing fancy. So we get 294. Right. So I get a final. I have a 294. Is it 295 or 294? It's 294. All right, so that's 294. However, this is still v squared, so I still need to play around with it because I have v squared on the other side. So I have a vf squared this side, so I need to square root both sides, so I'll end up having a actual vf. So 294 squared, if I grab the calculator again, there he is. Who's the good boy? Okay, so the square root of 294, like so, that's just 7 root 6 as a third. However, that's just about 17,15, since I'm at my final answer, 17,15. Okay, we'll set that aside. So that's just 17,15. Okay, then the next question, number 2. If the effects of air friction are not ignored during the fall of the cricket, how will the value calculated there change? Well, it would be lower because it would slow it down. Because of that, it would move slower. That's the idea. So this would just be lower. Okay, that was a very much dumb question. Anyway, so the one that follows says, the cricket ball is in contact with the concrete pavement for 0.8 seconds. Calculate the effect of air friction. Take downwards motion as positive. Cool, I'll take downwards motion as positive. So this is an impulse question because we have time involved in this case. Okay, because they just said calculate the impulse of the cricket ball on the pavement. So I'll be making use of F net. I'll be saying F net delta P, and not delta P, but rather delta T. So this is F net delta T, and this is equals to delta P. So what is the issue now? Well, the issue is to calculate my impulse, I need my momentum. And for my momentum, the problem now is the fact that my change in momentum, I need my final velocity and my initial velocity. However, I don't know my initial velocity. I don't know the velocity that it used coming from up, coming down. I don't know that. How much velocity did I throw this ball with? That I don't know. So I need to first calculate that initial velocity. And the first formula there works for that. So I'll use that formula. So that's a v squared. That's a vf squared equal to vi squared plus 2a delta y. Nothing fancy. Then let's make the substitutions. The final velocity. So at this point in time, I'm focused on the projection, the first projection it used to go up until it reached the maximum height. That's what I care about. When it started that projection, we know that when it reaches its maximum velocity, its maximum height, at that maximum height, the velocity is 0. So I wanted to reach a 0 velocity. However, the initial velocity is essentially what I'm trying to calculate. So that's just a vi squared. And this is equals to 2. And the a, that's just gravitational pull. That's just 9,8. You know this. That's 9,8. And then the y, look at this right there. There is that first projection there. Did you see that? So it's a bounce there. So that's within its first bounce. It then covered the four. The four. Okay. So that's what I'm calculating. I'm calculating the contact with the pavement that it had. So this thing was thrown up and then boom. That's what happened there. So hence I'm using that y of 4. Okay, then because now I'm going to solve for vi. So I'll let the calculator do the work because it's better than yours. So if I grab it, so there he is, who's the good boy. All right, so I'll make the substitutions. 0 squared is equal to, well, vi, I don't have vi, so I'll make use of x. So that's just an x squared. Okay, plus, I don't, what am I doing? Okay, yes, vi squared plus 2 and 9,8, and then I'm going to have a negative 4, in fact, because I'm covering it from the bottom going up. Okay, and then I'll get I have a syntax error there because I'm supposed to be hitting the solve button instead. Genius. Okay, so I get like up about 8,85 there, and I need to change this. 4 has to be a negative. Okay, so I get a vi of 8 comma 8 5. Remember they said take downwards as positive. That's why this one is negative. Going down was what they told us to take as positive. So because this ball is going up, we would have the distance being a negative. So proceeding, now that I have my vi, I can actually make use of my impulse formula, which is the one that I've got there. So to do that, I would do the direct substitution there. So first things first, I've got my f net delta t, and this is equal to delta p. Nothing fancy. Now to make those substitutions, I'm finding impulse. Remember the whole f net delta t represents time. Then here all I have is m, okay, and this is multiplied by vf minus vi, just to simplify things. And then the mass of this ball is said to be 156 grams. The problem there is it's not in kilograms, so I have to change it to kilograms. And 156 grams in kilograms is just 0.156. Okay, what's my final velocity? Well, my final velocity, I just calculated that. My final velocity, I got it to be negative 8,85 minus. And then what happened? Well, I have the 17,15. To understand that substitution, once again, here's the projection. You were told it's dropped from point A. So it's dropped from that tall building that is 15 meters high. It covers the 15 meters and then it strikes the pavement, okay, and then it bounces to a maximum height of 4. That's what happens. It's just boom, that's it. So we used that projection, we use the up projection that it goes with. So when we're looking at the projection where it covered the 4 meters, we'll have to then realize that as it bounces back off, its final velocity from its previous projection becomes the initial velocity of the next. I don't know if that's making any sense in that case, but if you look at the previous question that we did, in the previous question, the previous calculation, we calculated the velocity that it strikes the ground with. So what's the velocity that it strikes the ground with? The velocity that it strikes the ground with is the one it left point A with. However, for it to come back, the final velocity of that previous one became the initial velocity to come back up, and that's what we were doing. So the final velocity we calculated before becomes the initial velocity of this one, okay, and then the final velocity is that's basically the substitution that we just made now. So to proceed and finish that off, we'll then simplify that. So I'll grab the calculator and let the calculator do the work. So here's the good boy. So to do this, we're going to do that substitution of 0,156 right there. No, there 0,156 minus 8,85 minus 17,15, which was the one we had from the previous question. Then I'll close that off the bracket and then get my direct answer. I get about 4.05, that's 4.06, and negative, so this is an upwards because we're told to take the upwards as let me see that again. We get a negative, okay. We're told to take downwards as positive, so because it's reflecting back up, then I'm having an upwards out of the negative answer. So I would have I got negative 4.06 newtons, which means this is 4.06 newtons upwards. Okay, there we go. All right, because they said take downwards as positive, because I got a negative, it has to be upwards. All right, then we're told to sketch the position versus time graph for this projection. Okay, so okay, I think I've skipped the question. Oh yes, calculate the net average force exerted by the pavement on the cricket ball. So what is the net? Well, the net force, the net force. So the net force, so I'm just gonna have it here. So okay, I'll just put a dot for that, honestly. Okay, so the net force, this very much denotes back to my impulse. I'm essentially just calculating the F net. Okay, I'm calculating the F net. We know F net delta T is equals to delta P. This we know. So let's make our substitutions there. What I just found right now is impulse. Okay, and impulse is the same thing as the change in momentum. So in place of change in momentum, I'm going to substitute in my 4.06. Okay, and then here I've got F net. However, my delta T, I'm told that this thing was in contact with the ground for 0.8 seconds. So that's just 0.8 seconds. And then I have to solve for my F. And to solve for my F, I'm just going to make the calculator do the work. So we'll bring the calculator back, and where's my calculator? Okay, there we go. So for this, that's because I don't have F, I'll use X, and then we've got 0.8 equal to, and this is equal to 4.06. So this is 4.06, and then shift solve equal to, and that's just 5.07 for that. All right, so we'll take that out. So that's 5.008 approximately, or 5.07. Yeah, so our F net is then 5.07 newtons. That's our F net. Beautiful. Then the next one after that wants us to draw the position versus time graph. Okay, use point A as the 0 position and proceed. So we'll just draw roughly the axis. So we'll have our time in seconds on the x-axis, and then here we've got our position, our delta y, and this is in meters. Okay, so this thing started at 15. Okay, so I'm gonna have the value 15 there. It started 15 meters, then it came and it bounced. I don't care about the time, I was not given times in this case. However, after that it spent some time, so I cannot go immediately outwards after this. I have to give it some time and then bounce off, and then it bounced off to the height of 4 meters, and there's my 4. So I'll do that. This is a fairly easy and dumb question. Then there's an increase decrease, stay the same type of question there. They're saying the cricket ball is now replaced with a softer ball of a smaller mass. State how the net average force exerted by the concrete pave on the softer ball compares to that answer we got in 2.3.2. Okay, so they use a much softer ball where it exerts more force. Well, this will be smaller, okay? This will be very much smaller. What's the reason to that? Well, the reason for that, so I'm proposing that this would be smaller. And the reason for this is actually shown using the impulse momentum theory. The F net is inversely proportional to the delta T. So my F net is inversely proportional to the delta T. Okay, so they use the softer ball. It will take a much longer time. Because of that, it will exert a lesser force. Okay, and I've actually used a physics principle to explain that. So we cool. Then for the next question, we've got this interesting one. So on the right there, I've got my formulas, my equations of motion once again. So a boy kicks a ball vertically upwards from a height of 0.6 meters above the ground. So the ball is positioned there and then it's kicked up. Okay, and it covers 21 meters. The ball moves past the top of the building. It moves way past it and it actually goes on top of the building. It goes past the top of the building, which is 21 meters higher than the point where he kicked the ball. The ball hits the roof of the building 3.1 seconds after it was kicked. Okay, the ball bounces off the top of the building and comes to rest. Okay, let's take one question at a time. Write down the magnitude and direction of acceleration at point X. I don't have to think this one through because really acceleration is constant. It's always going to be 9.8 meters per second. You know this. This shouldn't stress you. This is velocity, not acceleration. There you go. 9.8 meters per second, and this is upwards at point X, provided there it's upwards. Okay, so next question, number 2. So we've got our number 2. Calculate the magnitude of the velocity with which the ball was kicked. So what am I looking for? Well, I'm looking for an initial velocity. What was the velocity that it left point X with? That's the idea. So I'm looking for an initial velocity, whereas I may not necessarily know the final velocity. So I'm looking for a formula that has initial velocity but no final velocity. You guessed it, it's this formula there. Okay, we're going to use that formula in this case. So delta y is equal to my vi delta t plus a half acceleration and delta t squared. Nothing fancy. I'm just copying the formula. Now let's make the substitutions. What is the total height that it has traveled? Well, it traveled 21 meters, so nothing fancy there. And vi is essentially what I'm trying to calculate, so that's just vi. And then what is the time? The time that it takes to cover that height is 3.1 seconds. Okay, so it took 3.1, that's my time, to cover that 21 meters. It took 2.1 seconds. Okay, then plus a half. Okay, a half, and then my acceleration, I can't stress this much, however it becomes a negative 9.8, because remember it is slowing it down when the ball is going up. That's why we have a negative. It's subtracting from the velocity. That's why it is a negative 9.8, as opposed to when it is coming down, it is a positive 9.8. And then the time, our time, we still have 3.1, and this is squared. All right, then I'll let the calculator do the work. So we'll bring back the calculator, good boy. Then we'll let it do the solving for us. So to let it solve for us, I'm just gonna make the substitutions that I actually have there. I've got a 21 on this side, so it's just 21. This is equal, so I'm just going to use this equal. So I'm just jumping the gun here. You have to of course solve things manually. So 21 and then I don't have vi, so I'll make use of x. Okay, and this is multiplied by 3,1, which was my time. So 3,1 plus a half, so that's just the 1/2. Okay, and this is multiplied by my acceleration of negative 9,8. Okay, my negative 9,8 multiplied by 3,1, which is my time squared, and then shift solve equals, and we get 21,96 approximately. 21,96. I'm gonna get rid of that, and we get 21,96 as our initial velocity. 21,96. Goodness gracious. 21,96. And this is meters per second velocity. Okay. Next question. Calculate the maximum height that the ball reaches above the ground. The maximum height. That 21 meters that you have there, that's not what the maximum height is. The maximum height we have to consider after it has passed the top of the building. We have to consider that. Okay, so what we're going to do first is we're going to calculate the height that it travels. Okay, that includes the ground as well. So what we're going to do firstly do is we're going to calculate our y, okay, our delta y, the total y that it actually travels in the case where it reaches its turning point. So we want to know this one, we want to know this height. That's what we want to do. We want to know that height. Okay, so remember at this point that our velocity is 0 because that's the turning point. So my final velocity for this question would be 0. My initial velocity, this is the velocity it left the ground with. I just calculated that one now, and then we're home and dry. So I want a formula that has initial velocity, final velocity, but should help me calculate a y. Okay, and the formula that does that is this one. So we're going to use that. So this is my number 3, and this is just step 1 of it. So vf squared will be equal to vi squared, okay, plus 2a delta y. Okay, then we'll make the substitutions for that question. So my final velocity is essentially my turning point, so that's just a 0 squared, and this is equals to, what is my initial velocity? I just calculated that previously in this question there. That's just 21,96, and this is squared, plus 2. What is the acceleration? Remember, it's going upwards, so my acceleration shall be negative 9,8. So I'm gonna have a negative 9,8 in there. And then what's my y? That's what I'm calculating there. Then to solve for y, we're going to use the calculator. Because my calculator is capable of solving, I will do it. And of course, you have to do it manually. So I've got a 0 squared. I honestly don't know why I put in the 0 squared, but anyways, then I've got a 21,96 squared. So let me put in brackets to clean this up. So take that back. Squared plus 2 multiplied by a negative 9.8, and this is multiplied as well by the unknown x. So that's our unknown we're trying to find, which is our y. Shift solve equal, and then we get our answer there, which is 24,60. So that's just 24,6, not to make things fancy. So 24,6. So that's what we're going to have for our y, the total projection. So our delta y is going to be the total projection, which means this whole thing here is that 24,6. However, this is not my final answer. Okay, they want the maximum that it has reached above the ground. Okay, so I'm going to include the ground as well. So the one that it did would be the 24,6 plus the ground itself of 0.6. Okay, and to get that we would have about 25.2 meters. Not much of fanciness there. Anywho, next question. Refer to the sketch and state whether the collision of the ball on the roof is elastic or inelastic. This is a pretty dumb question, but if we look at it, this is going to be an inelastic. Why is this inelastic? Well, it's inelastic because it bounced, it did a first bounce, it went up, and then it did its first bounce. Its first bounce is not the same, its height was not the same when it bounced the second time. That's as inelastic. If it was elastic, would be having a bounce like that where they're perfectly elastic. However, this one is like that, so that is an inelastic. Okay, then the one following, sketch a position versus time graph. I cannot stress much, but let's see. So they're saying we have to start from the position X and so on and so forth. So I'm just going to roughly create my axes. So this would be somewhat like that. Okay, so here I'm going to have my time in seconds, and here I'm going to have my position in meters. Okay, so this thing starts off at so here we're doing a position versus time, or yeah, a position versus time graph. So it starts off at a negative 21, so it was 21 meters away from its end point, hence I've started with it as a negative. Then it's kicked and it covers about 3.6 meters. Okay, so 3.6 meters. Okay, it covers a good old 3.6 meters, and after the 3.6 meters it then comes back down, then it bounces again while it's at the roof of the building, and done. And we have to consider our times in this case. So 3.1 seconds it finished this projection, and then afterwards it comes to a rest at 4.2 of time. Right, and these are just values that I was given there. Okay, so that answers the question, easy as pie. And that is vertical projectile motion practice problems. And of course you have to practice a couple of more other question papers. So vertical projectile motion done, and I will see you in the next chapter.